Hello, everybody. So today's video, we're going to be looking at the worksheet that has a bunch of things on it. It has molar mass, percent composition, empirical molecular formula, mole conversions. I'm not going to go over every single problem because some sections really are self-explanatory by looking at the answer key, but I will do at least one problem from each section as a review. So the first 8 problems are just calculating a molar mass. So as a reminder, you are going to use your periodic table. You're going to multiply the subscript times the mass plus the subscript times the mass, add it all together. I tend to go 2 past the decimal. Some other teachers may require 3 past the decimal, but 2 past the decimal tends to get you enough significant figures for what you need for your answer. So the molar mass of this would be 12. I look on my periodic table. Carbon is 12.01, so I multiply those together. I have 26 hydrogens. Molar mass of hydrogen is 1.01. I hit it all into a calculator, and I get 170.33, and the unit is grams per mole. Be careful. I would hit the molar mass in twice when you're taking a test to make sure you get the correct molar mass, and make sure that you're not making silly mistakes. Okay, I'm only going to do 5 and 6 on the mole conversions because these involve 2 steps. So question 5, we have a certain mass of C12H26, and we want to know how many moles of carbon atoms there are. So this we're going whole to the part. In order to do that, remember, we need to look at the chemical formula. So what this means, these subscripts, it means that I have 12 carbons per every 1 C12H26. I have 26 hydrogens per every 1 H26. That works when I am in a unit of individual molecule. That works when I'm in a unit of moles. So if I can get the moles of this whole thing, then I can very easily convert that to moles of carbon. So we have 52.89 grams of C12H26. First step in just about any problem in chemistry is get to moles. Well, we know how to do that. Grams of the C12H26, we can go to moles because we got the molar mass in question 1 on the previous section. It was 170.33, but this is moles of the whole thing. Now I want to get to moles of just carbon atoms. So moles of this comes down. Moles of carbon goes to the top. And now I'm going to use the relationship of the 12 carbon to 1 mole of the total. So my units are going to cancel. And I get an answer of 3.726 moles of carbon. The second question here, question 6 on the worksheet, we have a certain number of molecules of SF6 and we want to know what mass that is. Mole isn't mentioned. I'm going to need 2 conversions. Molecules represents a thing, so we're going to be using Avogadro's number. Mass represents, obviously, a mass, so we're going to use molar mass. We don't care about the volume because it's not mentioned here, and we're only going to use those 2 conversions. So now I set up 2.93 times 10 to the 24 molecules. I'm going to put it over 1. Molecules comes down. Mole goes to the top. Because I'm going from mole to a different unit, 1 goes next to mole, and this is where we're going to put Avogadro's number. Mole comes down now, and now I can go to the unit of grams. So because I'm going from a unit of mole to some other unit, not to a different unit of, not to another unit of mole, this would be an example up here of going from a mole to a mole. Notice I don't have a 1 next to mole there. But here, 1 mole, we look up above, SF6 has a molar mass of 146.06. My units cancel. I do the math, and I get 711 grams of SF6. 6. All right, so here we have 2 examples from the percent composition section. And again, I'm not going to go over every percent composition because it's really easy. It's just hitting into your calculator. You just have to be careful that you hit all the buttons incorrectly because it's very easy to make a mistake. It's super easy to do, but it's also very easy to make a mistake. Now, the overall molar mass of sucrose, by summing up all the molar masses, is 342.30. That unit is grams per mole. Now, whenever we do a percent composition or any percent, it's always part divided by whole times 100. So to get my percent carbon, I'm going to put the mass of carbon that I have using molar masses. So it's going to be 12 times 12.01 on the top. And then the total mass is 342.30. Multiply that times 100, and I get 42.1%. To get my percent of the hydrogen, I take the mass of the hydrogen and put that on top. So it's 22 times 1.01 over the total molar mass, 342.30, multiplied by 100, and I get 6.491%. And then to get the mass of the oxygen, it's going to be 11 times 16 divided by the total, 342.30, multiplied by 100, and I get 51.42. And then check your work and make sure they add up to 100, which these do. All right, number 6 is using the percent composition as another method to determine the amount of a certain element in a sample. So we can use train tracks and use the ratios of our subscripts, which the ratios here, or we can just use a percent composition. So if I know that a sample of sucrose always is going to contain 51.42%, all I have to do is multiply the mass of that sample times the percent oxygen, and I will figure out how much oxygen I have in that sample. So if I have 250 grams of sucrose, I multiply that times 51.42%, and I get a mass of 128.6 grams. All right, I am going to do all of the empirical and molecular formulas because these have a couple more steps, and I want to just go through so that you have these all worked out. So we have this substance, monosodium glutamate, which is MSG. Some people are allergic to it. It's very common in Chinese food. And we have found that a sample contains 35.5% carbon, 4.77% hydrogen, 8.29% nitrogen, 13.6% sodium, and 37.9% oxygen. And we want the empirical formula. So this type of problem in chemistry is one where you just follow the steps and you get the answer in the end. Okay? Just do step 1, step 2, step 3, boom, you're done. Okay? Now you can also use the poem, percent to mass, mass to moles, divide by smallest, multiply till whole. So we're given our percentages here. So if we assume 100 grams total, these percentages become our masses. So for carbon, we have 35.5 grams. For hydrogen, we have 4.77 grams. For nitrogen, we have 8.29 grams. Sodium, we have 13.6. And oxygen, we have 37.9. So that's the first step, percent to mass. Done. Now, mass to moles. We convert each of these values to mole values. So 1 mole of carbon has a mass of 12.01 grams. I get that from the periodic table. 1 mole of hydrogen is 1.01. 1 mole of nitrogen is 14.01. 1 mole of sodium, 22.99. And 1 mole of oxygen is 16. So I hit this all into my calculator, and I get 2.956. I get 4.723, 0.5917, 0.5916, which is essentially the same number, and 2.369. So this tells me how many moles of each of those elements are in that compound. Now, since we've already talked about that the subscripts represent a mole ratio, I can now turn this into a mole ratio by dividing by the smallest. So I'm going to divide by 0.5916, divide everything by that value. It helps as you do these problems, do all the work, show all the work so your teacher can see what you're doing, and then you're likely to get full credit. Now, be careful as you do these, because if you round these values too early, you're going to get a weird mole ratio at the end. There are no significant figures with these problems because you spit out a chemical formula at the end. So you can report as many digits as you want, and that does help at the end. Now, at the end, we are getting a ratio of 5, 8, 1, 1, and 4. Now, if you get a value at the end, I think if I recall, this is really like 4.99 something, and this is like 7.99 something. You can round that to the closest whole number. If you get like 4.8, you can't round that. That's not close enough. You would then have to multiply by a factor to get a whole number. So within the poem, we did the percent to mass, we did mass to moles, we did divide by smallest, and we don't need to multiply till whole because we already have all the whole numbers, and these become our subscripts. Now, when you go to write the chemical formula, you can put the elements in the order in which they're given in the problem. So it's going to be C5, H8, N, Na, O4. Remember to write these as subscripts, and remember that if it's an element with 2 or more letters, the second letter has to be lowercase. So that is my empirical formula. Okay, the second empirical formula problem, we're not given percent values, we're given gram values. So the percent to mass part in the formula is already done for us. I'm sorry, in the poem is already done for us. So all we have to do is nickel, carbon, nitrogen. So we have 10.52 grams, 4.38 grams, and 5.10 grams. So we just start with the masses that are already given. Now we jump in mass to moles. So 1 mole, nickel has a molar mass of 58.69, and we get 0.1792 moles. Carbon, 1 mole, has 12.01 grams for a mass, 0.3647. And remember, I'm not rounding this too early so that I get a appropriate ratio at the end. 1 mole of nitrogen has a mass of 14.01 grams, and we get 0.3640 moles. So we've percent to mass, check. Mass to moles, check. Divide by smallest. Sometimes people forget this step, and it really ends up with a very difficult problem at the end. You always have to remember to divide by the smallest so that we get that ratio. And so we get a 1, a 2, and a 2. So what our empirical formula is going to be, we don't have to multiply this times any multiple to get to a whole number. So it's going to be Ni, C2, N2. And there's our empirical formula. Okay, this problem is an empirical formula problem, but it's also a molecular formula problem because they're giving us a molar mass. So we're going to have to do one more step at the end. Remember, a molecular formula is multiples of an empirical formula. So we're going to have to figure out what that multiple is at the end of the problem. So we're given the percent composition. So we're going to do the first step, which is percent to mass. So we have carbon, we have hydrogen, we have oxygen. So we have 39.12 grams of carbon, 8.75 grams of hydrogen, and 52.12 grams of oxygen. Now we're going to do mass to moles. So 1 mole carbon is 12.01. 1 mole of hydrogen is 1.01. 1 mole of oxygen is 16. I get these values from the periodic table. So now I get 3.257 moles. I get 8.663 and 3.258 moles. All right, so mass to moles is done. Check. Divide by smallest, 3.257. I get 1. I get 2.66, and I get 1. So this is one I cannot round this. I cannot round it to 3. I have to multiply by a factor. And the factor that I need to multiply by is 3. So I'm going to get a 3, an 8, and a 3 for my subscripts. So it becomes C3H8O. And this is my empirical formula. But remember, to get my molecular, I need to figure out what the factor to multiply by the empirical is. So I'm going to take the molar mass of my molecular, which is given in the problem, divide by the molar mass of my empirical, and I get some whole number. That whole number tells me how many empirical formulas there are in my molecular. So I calculate the molar mass of my empirical. So the molar mass of my empirical is 92.09. Now I figure out my factor. So it's 92.11, which is the molar mass of the molecular, 92.09, which is the molar mass of the empirical. So clearly my factor is 1. So I only have 1 empirical in my molecular. So my empirical is equal to my molecular, which is C3H8O. Okay, question 4 is another molecular formula problem where we're going to have to figure out the factor at the end. How many empiricals are there in the molecular? So this number right here, we're going to put aside and deal with at the end after we have determined our empirical formula. We are given percentages. So the first step is percent to mass. So we have carbon, hydrogen, and oxygen. Carbon is 75.7 grams. Hydrogen is 8.80, and oxygen is 15.5. Then we're going to convert to moles. Hydrogen's 1.01. Oxygen is 16. So we've done percent to mass, check. Mass to moles is what we're doing now. So we get 6.303 moles. We get 8.713 moles and 0.9688 moles. Okay, the third part of the poem is divide by smallest so that we can get our mole ratio. So we divide by the 0.9688. This is 1. This is 9. This is 6.5. If I get a 6.5, I cannot round it. I have to multiply till whole. And the factor that I need to multiply by is 2. So it means I'm going to have 13 carbons. I'm going to have 18 hydrogens, and I'm going to have 2 oxygens. Now that is my empirical formula. but I have to compare the molar mass of this to the molar mass of my molecular to see how many empiricals I have in my molecular. So molar mass of the molecular goes on top. Molar mass of the empirical goes on the bottom. So the molar mass of the molecular is given in the problem. That's 206. I calculate the molar mass of my empirical, and I get 206.28. So just like the previous problem, my factor is 1, so which means my molecular is my empirical. So my molecular formula is C13H18O2. All right, this problem isn't exactly an empirical formula as far as using the poem, but it's sort of an application of, again, a percent and the formula and trying to figure out what's in the substance. So we have this formula, M2O, and we know that it contains roughly 17% oxygen. And I want to figure out what the molar mass of the compound is, and ultimately I want to figure out what M is. Well, we know a percent composition formula for oxygen. So my percent oxygen is going to be my mass of oxygen divided by the molar mass of the whole thing, which is M2O. Well, I'm given the percent oxygen in the problem. I can get the mass of oxygen from the formula. So therefore, I can figure out the molar mass of M2O. So 16.99% is going to be the mass of oxygen. I only have one oxygen, so 16 goes on the top. The molar mass of M2O goes on the bottom. Multiply by 100. I forgot that part over here. And now I need to solve for the molar mass of M2O. And that's just algebra. You can look at the answer key for how to do that. And my molar mass of M2O is going to be 94.17 grams per mole. So that's the first part of the problem. Now I want to figure out, well, what is M? In order to do that, I'm reversing the molar mass formula because the molar mass of this substance is going to be 2 times the mass of M plus 1 times the mass of oxygen. So the molar mass of the whole thing is 94.17, is 2 times the mass of M plus 16. When I solve for M, I get 39.09. I look at my periodic table, and I find that decimal number on the periodic table, and that is potassium. All right, for the last problem, number 6. I really like this type of problem because it ties a bunch of things in together. So it's a combustion analysis problem of DDT, which contains carbon, hydrogen, and chlorine. DDT is a insecticide which kills mosquitoes. It was designed to combat malaria. And so when we have this sample of DDT burned, we get a certain amount of CO2 and a certain amount of H2O. We also, in a second experiment with the same exact mass, determined that it's 50% by mass chlorine. And so what this problem is doing is it's breaking up, getting the individual moles of each substance, of each element, into individual steps, and then getting the empirical formula at the end. So make sure you know how to do multi-part problems, because multi-part problems, part B refers to part A sometimes, or part D refers to something that was mentioned in the main paragraph. So make sure you read the whole problem and understand where to get all the information. So A, what is the number of moles of carbon? So all of our carbon in DDT was converted to CO2. So I need to figure out how many grams of CO2 are in this mass of CO2. I'm sorry, how many grams of carbon are in this mass of CO2. So if I have 8.692 grams of CO2, I'm basically going to set up, I'll erase this because I'm actually going to do this percent-wise. I set up a percent carbon, a percent composition formula, which I'm going to multiply times the mass. So you can do it this way, or you can go back and do a mole conversion that like we learned at the beginning of the video. So I have 12.01 grams. That's the molar mass of carbon. That's in CO2. Divided by 44.01 grams per mole, actually, which is the total molar mass. This is the way to get the percent carbon in CO2. And then all I have to do is multiply that. I'm having problems here with my erasers. And then all I have to do is multiply that times the total mass, and I can get the grams carbon. So when I multiply that, I get 2.372 grams of carbon. But the problem is saying how many moles of carbon is that? Okay, well, I know how to do that. I can just take that and convert to moles by dividing by the molar mass, and I get 0.1975 moles of carbon. Okay. B, what is the number of moles of hydrogen? Okay, well, it tells us that I have that many moles of water. Well, I can convert to grams of water and then do a percent composition, but that would be a little bit too much work. I do know that I have 2 moles of hydrogen per 1 mole of water. I have that ratio, so I can convert the 0.06339 moles of water, and I can very easily get moles of hydrogen because 1 mole of water contains 2 moles of hydrogen. So I get 0.1268 moles of hydrogen. All right, C, we want moles of chlorine. Well, it tells us up here that if we have a 5-gram sample, both of these started with 5 grams, so 50% of that sample is chlorine by mass. Well, 5 grams times 50% by mass of chlorine means I have 2.5 grams of chlorine. And then I can very easily convert this to moles. So 1 mole of chlorine has a mass of 35.45 grams, and I get 0.07052 moles of chlorine. Now D, when it says, what is the empirical formula? Well, I need to go and look at A, B, and C, because now I know the moles of each of my individual elements. I'm at the point now where if I divide by the smallest, I get the mole ratio. So I have carbon, I have hydrogen, and I have chlorine. Carbon, I have 0.1975 moles. Hydrogen, I have 0.1268 moles. And chlorine, I have 0.07052 moles. So I'm at the point now where I need to divide by smallest. The smallest is 0.07052. So I divide all of these by that value. And I get 1, I get 1.8, and I get 2.8. You cannot round this. It's not close enough to a whole number. So now we're going to have to multiply by whole. The closest value, the lowest number to multiply this by to get a whole number is 5. So what I'm going to get is 14 carbons. I'm going to get 9 hydrogens and 5 chlorines. So it's C14H9Cl5. And there is my empirical formula for DDT.